Okay, so we're going to look at the first concept in Unit 4 today, and that is simple harmonic motion. All right, simple harmonic motion, very simply, is any motion that repeats itself over and over and over again in exactly the same fashion. All right, so a pendulum, and see, I'm getting double usage out of my ghetto physics thing here, okay? Triple usage, that's right, because I used it for horizontal and vertical, and now it's a pendulum on top of it, okay? So a pendulum is an example of simple harmonic motion because it'll simply keep doing the same thing over and over and over again. Now, why will it keep doing that same thing over and over again? Okay, nothing's stopping it, okay? But, I mean, if I don't start it, nothing happens, right? So what first has to happen is the object, whatever it is, has to be moved away from what we call the equilibrium position. Okay? The equilibrium position for a pendulum is straight up and down because that's where it would sit normally, right? If I disturb it from that equilibrium position, I have to do what? I have to do work. I have to give it some energy. Okay. Once I've done that, though, if this was a perfect world, okay, that pendulum would just keep swinging back and forth, because there's a force that's trying to bring it back to the equilibrium position all the time. In the case of a pendulum, that force is gravity. Okay, so it's always trying to bring it back to equilibrium. We call that a restoring force. For any simple harmonic motion to occur, there has to be a force that's trying to bring the object back to equilibrium. For simple harmonic motion to keep happening, equilibrium can never be restored. If it was restored, then the thing would stop. Okay, but for an object undergoing simple harmonic motion, the restoring force never actually restores equilibrium because gravity will pull this thing right past equilibrium. Okay, or actually it'll pull it to equilibrium, but then it'll go right on by because we've given it all this kinetic energy. Okay, it'll go right on by and turn that back into potential energy, and then it'll swing back through as the restoring force slows it down, starts to bring it back to equilibrium. It passes it again, and it just keeps going. Okay, back and forth, back and forth. Everybody with me there? All right, I'm not going to make anybody cluck like a chicken or anything like that because I don't know how to do that, although I think it's cool. Yeah, hypnotize you. Yeah. The pendulum. Yeah. I know it's Monday and I'm not that funny, but okay. All right, so key points for today. Understand what simple harmonic motion is. It's any movement that can repeat itself over and over because of a restoring force. Okay, how can it happen and be maintained? Well, first off, something has to be disturbed in the system. There has to be work done. And then the restoring force has to continue to try to restore equilibrium. Okay, and then we're going to look at two common examples. We're going to look at a mass on a spring. Okay, if I put a mass on a spring and I push it away and then let it go, it just bounces back and forth, okay? And obviously the simple pendulum, right, is the other example. Those are the only two examples of simple harmonic motion we'll look at early on, but we'll also look at waves in the second half of the unit because waves are produced by something oscillating with simple harmonic motion. That's the second half of the unit. All right, so a playground swing is a pendulum, okay? It moves back and forth, okay? If you've ever pushed your little brother or sister or whatever, okay, on the swings, okay, then obviously you get this pendulum action going on. But in the real world, which is where, playground swings are, what does the kid have to keep doing? Yeah, they got to pump their legs, right? Back and forth, otherwise friction will cause the thing to stop. Okay, but gravity is the restoring force for the child on the swing. Okay, for a mass on a spring, okay, that's the middle picture here. If I take this mass from its equilibrium position, which is marked here by this dotted red line, okay, that's where the mass would sit if it was undisturbed. Okay, I pull the mass away from that. I've done work, I've put energy in the spring, and now this thing will oscillate back and forth, as you see in the picture here, continuing to pass through equilibrium as it oscillates back and forth. Okay, same is true for any string instrument. Okay, if you play the guitar or the violin or whatever, okay, you disturb the string, okay, by plucking it or putting the bow across it or whatever, okay, you cause it to vibrate back and forth. It continues to pass equilibrium. Okay, a tight string is essentially a spring. Okay, it works on the same principles, and it just oscillates back and forth, and the vibrations are transferred into the resonance cavity of the instrument, okay, where they are naturally amplified, which we'll talk about how that works later on in the waves unit, okay, and then they come out and you hear the sound. All right, everybody okay with those ideas? All right, so those are just examples of simple harmonic motion. Okay. All right, so in any case of simple harmonic motion, there is an equilibrium position. Okay, and we need to know that there's always going to be an equilibrium position. If the object's pulled away from equilibrium, okay, a force in the system tries to pull it back. So if it's a mass on the spring, it's the spring trying to pull it back. If it's a pendulum, okay, then it's gravity trying to pull it back. If it's a string on a guitar, it's tension in the string, okay, trying to pull it back to equilibrium. All right. Now, when the object is at its equilibrium position, which is again this one here marked by the red dotted line, what's the net force acting on it right there? It's at equilibrium there. What would the net force be? 0. Yeah, the spring in this case is neither stretched nor is it compressed, so it doesn't exert any force. Okay, it's not until it's disturbed from equilibrium position by doing work on it that it has the ability to exert any force and thus try to restore equilibrium. Okay, and that could again be the stretch of a guitar string or a spring. All right, and obviously the more you tighten a guitar string, okay, the more it wants to return to equilibrium, and that actually changes the sound that it produces. Okay, everybody all right with that? We know what an equilibrium position is, right? At equilibrium, the net force is 0. And again, it's the same for a pendulum, right? If I've got this thing just sitting at its equilibrium position, there's no forces trying to bring it back here. It's already here, okay? It's when I bring it out to the side that there's now a gravitational component that acts along the arc that's trying to bring it back to equilibrium. Obviously, gravity wants to pull it straight down, okay? But there's a component of gravity that acts along that pendulum arc, okay, that causes it to return to equilibrium. Now, something about the pendulum, okay? When I use the whole length of the pendulum, okay, here, versus, what do you notice about the pendulum? Yeah, well, it's not faster, but the period is shorter. Yeah, it's shorter. When the pendulum is shorter, the period is shorter. When the pendulum is really long, right, it travels farther. So it's naturally going to have to take longer to make the oscillation because it's gravity that's pulling it, and gravity affects it equally whether it's really long or really short. Okay. All right. Okay, so for simple harmonic motion to occur, and this is important, you'll want to highlight this in your notes, okay? The restoring force has to vary linearly with displacement from equilibrium. So that means the farther from equilibrium I disturb the object, the harder the restoring force has to pull or push, depending on what force it is. Okay, and it has to vary linearly. So if I double the displacement from equilibrium, I need to have twice as much restoring force for this to be true. Okay, if it becomes exponential, okay, or it starts to become nonlinear, then I'm not going to get harmonic motion. I'll get motion, but it won't be harmonic. You can. Okay, so obviously for a spring, that's pretty straightforward, right? Because the force in a spring, okay, is kind of governed by this relationship you learned last year in Science 10, right? And we reviewed this year in dynamics, that work is force times distance. So the further I push this thing, I get linearly more force, okay? And when you did your lab last year, okay, with the rubber band, you pulled it with the spring scale, that's what you discovered. You got a force distance graph that was linear, okay? And that's kind of, we'll come back to that when we start talking about energy, but that lab is the basis for the energy part of simple harmonic motion, right? For a mass for a pendulum, okay, obviously gravity is the restoring force, but as we said, gravity acts straight downwards. But because this is an arc, okay, it does have a tangent component, okay, that is acting along the arc, all right? And that does vary linearly, okay, as we move through the arc, right? Okay. The motion of objects with simple harmonic motion can be described using some things we learned in the last unit, frequency and period. Okay, so the period is the time needed to repeat one complete cycle. Now, understand that one complete cycle actually involves going through equilibrium twice. Okay, so if we start like here at the maximum displacement, okay, we're going to move upwards through equilibrium to the maximum displacement upwards and then back to equilibrium. Okay, so we pass through equilibrium twice, okay, in any single oscillation. So the oscillation has to go from starting point to ending point, and those two ending points have to be equal. Okay. So if this one was returning, okay, the one full cycle would actually be back over here, okay, where the spring was stretched, okay, and it would look like this down here. All right, other things, okay, that describe simple harmonic motion, amplitude. Okay, amplitude is the maximum distance from equilibrium that the mass will achieve. Okay, or the pendulum will achieve if we're talking about a pendulum, but it's the maximum distance from equilibrium, okay, that the object can achieve. Now, when the object is at its maximum amplitude, how fast is it going? 0. Okay, and that's true for this mass on the spring, right? It's stretched the spring as far as it'll go, okay, and it stops before turning around and trying to return to equilibrium. Same thing here. Now we're compressing the spring. The spring can't be compressed anymore, okay, so we stop again, okay, and then return to equilibrium. All right, so at those points of amplitude or maximum displacement, our speed is 0. But, weird thing, our acceleration and the restoring force are at their maximum, okay? Because that's where the spring is most compressed or most stretched, where the pendulum is, gravity doesn't really increase, but the tangential part of it does, okay? Because it's getting more and more vertical. Am I confusing with the tangential part? Okay. Obviously, the force of gravity doesn't increase on a mass. The force of gravity is fixed on a mass. Okay, but as I get further from equilibrium, okay, the amount of that gravity that's actually pulling back to equilibrium increases. Okay, because when I get out to here, it's all right, because it can fall straight down at this point. Okay, but as I move along that arc, the amount of gravity that's actually acting towards equilibrium gets less and less. When it's here, it's perpendicular. Okay, gravity's not trying to pull it back to equilibrium, it's already there. Okay, all right. Okay, so that's a new term. Okay, we already know what period and frequency are, but amplitude is a new term. That's the maximum displacement. Okay, when we're back at equilibrium, we're moving at our maximum speed. Okay, we can't go any faster, but we just said the net force at this position is 0, which means the acceleration here is also 0, right? Because the thing's been pushing all the way to here, and then suddenly it's neither stretched nor compressed. It can't exert any force anymore until it goes past equilibrium again, and now it's starting to push back to equilibrium. Okay, everybody with me on that one? All right, so all simple harmonic motion is the same in principle. All right, if we're looking at a mass on a spring, the two things that can affect how far it goes and how long it takes to move are what? So I put a mass on a spring, I push it, and I start it moving. What two things in that system could influence how long it takes to go and how far it goes? Mass, and what else? Not so much the length of the spring, but something about the spring. What's that? How strict it is. Yeah, the stiffness of the spring. We call that spring constant. Okay, so the spring constant is how stiff is the spring. If we're talking about like the spring inside a pen, that's very small. If we're talking about the springs in your car, those are very stiff. Okay, they would have a very high spring constant. Okay, whereas the spring inside a pen would have a very, very low spring constant. So if I put the same mass, okay, let's say I put, well, probably 1 kilogram would destroy a pen spring, but let's say I put 50 grams on there, okay, then that spring would oscillate up and down, or back and forth, back and forth. If I put 50 grams on a car spring, right, it's hardly going to move at all, right? It would just be like this, be really, really quick. It's not going to move that car spring very far because the car spring is so much heavier. Everyone all right with that? So those are the two things that can affect the period of a mass on the spring, which is why they're in the formula that solves for period of a mass on a spring. So this formula is on your formula sheet, okay? The period of a mass on a spring is calculated by taking 2 pi and multiplying it by the square root of m divided by k, where m is the mass in kilograms and k is the spring constant. And the spring constant is measured in newtons per meter. That is, how many newtons would be required to stretch or compress that spring by 1 meter. Now, obviously, not all springs can be stretched or compressed a meter. That's just the units we use. Okay. Okay. If I want to manipulate this formula for mass or spring constant, what am I going to have to do? I'm going to have to square everything in order to get rid of that square root. All right, so if I'm solving for m or k, if I want to solve for either one of those, before I can move them, I have to get rid of the square root sign. So I have to go square the entire equation. Okay, now I can move things. T is squared, 2 is squared, pi is squared. Okay, and those two things that were under the root are now normal. Right, and now I can move them around and solve for them. Okay. Now, if we're looking at what this looks like, so the mass is on a spring here, as it oscillates up and down, it creates what kind of a shape? A sinusoidal wave pattern. Okay, this is why simple harmonic motion and waves are in the same unit. Simple harmonic motion causes waves to occur, right? When you pluck a guitar string and the string moves back and forth, it creates disturbances in the air that we detect as sound, okay? If an earthquake happens underwater, okay, it can move the ocean, okay, in a simple harmonic pattern, creating tidal waves, okay? Or just the wind blowing across the surface of the ocean can create disturbances that are harmonic within the waves of the ocean as well. All right, so that's what we'll be looking at there. All right, so the time it takes for this thing to complete one oscillation, so this is one full oscillation, okay, will be the period. The maximum displacement, okay, would be the amplitude. Everybody's all right with those two terms? Those are going to come up all the time in this unit. All right, so let's look at this first example. Sorry, Tanner. Yes, from one side to the other, it would be the same if it's a horizontal spring. If it's a vertical spring, no, because gravity will pull it further down. It doesn't help on the way up. So in that case, no, you don't get it, but we don't deal with the vertical ones, or we treat them like horizontal. Okay. All right, now what can change that amplitude, obviously, is how much energy gets put into the spring. If I push the thing further to start with, it's going to go further. Right? Okay, so our first example here, we have a mass of 0.2 kilograms attached to a vertical spring. We said we're just going to treat it normally, okay, with a tension of 28 newtons per meter. All right, so that's our spring constant, okay? This is our mass, okay? The ball is released from its equilibrium position. How long does it take for the ball to complete one cycle and return? All right, so this is a vertical spring. Doesn't matter that it's vertical for period. It only matters for energy, okay? So here's the equilibrium position, okay? And the mass was on the spring, so I released it. It would go down, and then it would come back up, and then it would return. So I'm trying to find how long it takes for that oscillation to occur. All right, so I have mass, and I have the spring constant K. So I just have to plug in those numbers into the formula. So T equals 2 pi times the square root of m divided by K. All right, and when I do that, I would get that that would take 0.53 seconds to oscillate one time. All right, that fairly straightforward? Not too difficult. Okay, now for a pendulum, Okay, we already saw that one of the things that can affect the period of a pendulum was the what? The length, right? Because if I shorten it, it obviously goes through one cycle quite a bit faster, right? What else can affect it? Okay, and that's usually the answer I get. Is usually people say mass, except that all things fall at the same rate. I could put more mass on here, it wouldn't change the period. In fact, we're going to do a little lab to prove it. Okay, the amount of mass that you put on here makes absolutely no difference to the period. But what's bringing it back to equilibrium? Gravity. Okay, if I change the acceleration due to gravity, would I change the period of a pendulum? Absolutely. If I did this exact same thing on the moon, this would go a lot slower, right? Because the acceleration due to gravity trying to pull it back would be 1/6 of what it is here. So it would go like, it'd be in slow-mo, okay? Right? But the astronauts actually did this. The Apollo astronauts actually took just a very simple pendulum, okay, to the moon with them, and they used it to essentially confirm the measurements that, or the calculations that that mission control had made for what the gravitational field strength of the moon would be. Okay, they just took a pendulum there. All they had to do was time a few oscillations and then plug it into the formula for a pendulum, which is T equals 2 pi times the square root of length over gravity. So it's very similar to the mass on the spring, except these are the two factors that influence the period of a pendulum, length and gravity. Now, there's actually enough of a difference on Earth for G that it can interfere with the timing of old-fashioned pendulum clocks. Okay, so how many people have like an old-fashioned like grandfather clock that's got the swinging pendulum in it? Okay, so obviously those don't just work on the pendulum, because if I just pulled the pendulum away and let it swing, it would only keep time for about a half an hour, and it wouldn't keep accurate time because it would constantly run slower and slower and slower until the pendulum stopped. So there's actually a spring inside, okay, that you wind up, okay, and it assists the swinging of the pendulum. So a true grandfather clock, okay, has the pendulum that's spring assisted to make sure that it keeps accurate time, but you have to adjust a couple of things inside depending on where you are to compensate for changes in acceleration due to gravity. Otherwise, your clock will run either fast or slow depending on where you are. Okay, so there's small adjustments that actually have to be made. Not that you would notice it over the course of a day or even a week, okay, but you'd notice it over the course of a month or so. You'd start to notice your clock was slow. Kind of like the clocks in this school, which have no reason to do that, but seem to get slower and slower all the time. Okay, they constantly have to reset them. I don't know why. All right. So L is the length of the pendulum in meters, and G is the acceleration due to gravity, obviously in meters per second squared. Okay, those two things will affect the period of a pendulum in the same way that mass and spring constant affect mass in a spring. Okay, so if we have a pendulum, okay, and it's located on a high mountain where gravity is 9.71 meters per second squared, the pendulum is a length of 1.55 meters, we want to calculate what its period would be. All right, so we would take the length and gravity and plug it into the formula here. So it'd be T equals 2 pi times the square root of 1.55 divided by 9.71, and we would get that the period of that pendulum would be 2.51 seconds. Now, terminology about a pendulum. Okay, the end of the pendulum, the mass that's on the pendulum, is called the bob. I don't know why. That's what it's called. It's called a pendulum bob. Okay, so we have pendulum bob SquarePants on the end of our pendulum here. Okay, because he lives in a pineapple under the sea. Absorbent and porous and yellow is he. Ah, you're going to have that song in your head all day. I'm not going to sing it because I won't do that, but no, I can't. No. Okay, so just so you know, if a question ever mentions like the bob of the pendulum is doing this, they just mean the pendulum as a whole, but the mass at the end is doing that. All right? Questions on how that one works? Okay. All right, now we're looking at, let's have you guys try this example here. Determine how long a pendulum has to be so that it'll swing back and forth with a period of 1 second with normal gravitational acceleration. All right, I'll give you guys a couple minutes on that one. Okay, so let's have a look at this one here, guys. So here's what we're given in this question. We're told what period is, so we have t, 1 second, and we have g, 9.81. So we have to manipulate t equals 2 pi times the square root of L over g, but we need to manipulate it for L. So the first thing we have to do to everything is square it. All right, so then we have t squared equals 4 pi squared times L over g. Now I can manipulate for L. I multiply both sides by g, divide both sides by 4 pi squared, okay, and I'm left with L. So L will equal, okay, 1 squared times 9.81 divided by 4 pi squared. All right, when I do that, I should get that it's 0.248 meters in length. All right, so I mean, obviously you guys have manipulated far more difficult things than this formula. So the algebra part of this shouldn't be too challenging for you.
What's going on?
This is a pendulum that they have at the Smithsonian Museum. It can swing for days. It's highly efficient, so there's very little friction involved. There's also these little things here help you to like measure how far it goes so they can compare how much it loses over the course of hours, days, whatever. Okay, but basically it's just like the most efficient pendulum there is. Okay, and it can swing for a very long time. Whereas most pendulum, like even this one here, like if I don't help it, which I was doing while it was swinging, it doesn't take long. It dies, right? So, you know, a pendulum is not a really efficient thing, okay, in the real world, unless you can eliminate friction, air resistance, and all that kind of stuff. Okay? And obviously, one that's on a rope is even worse because the rope can wobble, whereas if it's on a bar, it's going to be more efficient. You just have to make sure that hinge pivot point is very low friction. All right, try this one. Future astronaut lands on a planet with an unknown acceleration due to gravity. She finds that the period of the pendulum, 0.65 meters long, is 2.8 seconds. What is the acceleration due to gravity on this planet? Okay, so what we're given here is the length of the pendulum, 0.65 meters. Okay, we're told the period of the pendulum is 2.8 seconds, and we're looking for the acceleration due to gravity. So we got to take t equals 2 pi times the square root of L over g and manipulate for g. So first step, square everything. T squared equals 4 pi squared times L over g. So really all we have to do is switch g and t squared here in order to manipulate for g. So g will equal 4 pi squared times L over t squared. Most common mistake, forgetting to square t when they do this calculation. All right, so 4 times pi squared times 0.65 meters divided by 2.8 squared. So we got 4 pi squared times 0.65 divided by 2.8 squared. All right, gives us 3.27 meters per second squared, which is the acceleration due to gravity on Mars. Okay, so this would be Mars. Okay. So a pendulum would swing a lot slower. You would not take a grandfather clock built on Earth and use it on Mars. It would run really, really slow. It would lose hours a day. Okay. All right, questions on how that one worked? Okay, so this part of simple harmonic motion is like really, really easy. Okay, when we get into energy, we're actually going to start looking at how the stuff we learned in Unit 2 about conservation of energy also applies to both a pendulum and a mass on a spring. They are a system, okay, that has mechanical energy, so we simply have EI equals EF, but no longer for like a roller coaster or a sled. Now it's for a pendulum, which works just like a roller coaster or a sled, or for a mass on a spring, which doesn't use gravitational potential, it uses elastic potential. So we'll look at how we calculate elastic potential energy. It's easy, but the law of conservation of energy stuff is exactly the same for this as it was in Science 10. You just have elastic potential instead of gravitational potential. Okay, so there's lots of stuff in this unit that's easy, okay, or review from other units. All right, so we'll look at a couple more examples here. Okay, no, we don't need to do that one because that's just frequency and period. We already know that. And that's also the same thing. Okay. And that requires energy. We haven't done that yet. You know what? All those require energy. So we're going to do some off the worksheet here that don't require energy.